welcome to another installment of Data Skeptic Animal Intelligence. Today we're getting more on the mathematics side, getting into complex systems and how emergent behaviors relate to that. I'm joined as always by co-host Becky Hansis O'Neill. Welcome back, Becky.
Thanks, Kyle. It's good to be here.
So you helped me find Sebastian to come on the show today. Tell me a little bit about how you first identified his work.
So he was recommended by another guest. And as I went through some of his papers and work, it became clear that Sebastian really, in addition to his own work, helps out a lot of biologists, especially that are studying group decision making. Sebastian might not call it that, and you'll hear more about that in the interview. But basically, he's assisting us biologists who may not have the computational or mathematical know how in predicting behavior and looking at complex systems.
Yeah, it's interesting. He takes an approach to modeling different from what I usually do. I suppose depending on how you want to slice and dice the taxonomy, there's an infinite number of ways to model things, but in my head, there's kind of two camps. My camp as a machine learning person is you get a bunch of data, you feed it to an ML algorithm, and it finds a model, and the model is what it is. We can talk about its accuracy and its performance, but how it does its job, I mean, we can pry under the box and answer that, but there isn't like a formal X equals Y plus B kind of system, you know? Whereas that's the other school of thought in my mind that Sebastian seems to take of let's develop a model in like the classic physics sense, like 1/2 mv squared kind of stuff, you know, momentum in equals momentum out, and to assert your model and then see how it evolves, I guess.
And organisms are mere particles in the model.
True. Yeah, yeah.
What I love about Sebastian's work is it's often models that you can confirm or they're in conjunction with some kind of animal system or a slime mold system or something to that effect. So you can see if your model works. If your model predicts ants are going to do X, Y, and Z at a specific density of animals, cool, we can put those ants in a little cage and figure that out and set that experiment up. Or if you're looking at murmurations of birds, same thing. Do the birds do what you would predict they would do based on your model? So it's sort of like find and verify.
And there's another interesting point that's come up through a couple of these interviews, and we touch on today, is the idea that machine learning may or may not be helpful for a lot of this stuff. Like, it's easy to take videos now. Pretty much, you know, cameras are affordable, hard drives are relatively cheap. Sebastian and colleagues have, I assume, hundreds of hours of ants doing their thing, but still grad students are kind of looking at it and tagging it. Which, you know, I guess that could be frustrating from the grad student's point of view because they'll see something like the YOLO demo. I don't know if you know that one, but it's the computer vision that's able to in real time recognize tons of things. Here's a bike, here's a dog, here's a person. But even though it can recognize all those dogs, it's not trained to recognize their breeds, for example. Nor is it trained to recognize, you know, a flood that has 100 dogs and be able to count them. Yet it's plausible, right? ML should be doing that. It's just no one's focused on that side of the problem yet.
I know for me, I would do much better, and this is going to hurt. This is going to hurt the computer, the software programmers in the audience.
Sure.
If I had something with a GUI, so I could say map a little skeleton rig on my bee or whatever, and say the bee was doing this behavior, so I could make my own learning set, feed that in, and then upload a video, that I could probably handle. But right now I notice I'm going to get into programming pretty quickly, which I don't have a lot of training in. Setting up those data sets is not as easy as I just said. So I don't know if maybe we're just a little early to the party or what. Or maybe we just need more programming training to be able to set this stuff up.
Well, in my opinion, it's a mix of two things. You're right, you're early to the party. Probably about 5 years out, if I'm being cynical, because all the technology is there. It's like a last mile problem. Someone needs to figure out how to use YOLO or things like that as a base model, but then also, almost a separate problem, provide you an elegant interface where you can draw that skeleton on a bee. That's its own challenge, right? With 3D animation or how you have rigging and that kind of stuff,
Oh, yeah.
and then gluing those layers together somehow. How do we have an open source version of that model, pass it into the ML, and then train from there? So all very plausible, but we're getting there, I think.
Yeah. And it doesn't have to be beautiful. Like it could be complex, like Blender, and I would be more likely to take a crack at it.
Sure. Yeah, yeah. I mean, you could learn that, right? And if
Yeah, exactly.
it does the job, you'll put in the effort. So one property of Sebastian's work is that he'll look almost the way I think of a physicist looking at gravity. We have these base equations from relativity, or in his case, the equations he came up to describe behavior. And then it's a question of what does the math look like under different circumstances, different parameters, different cases? Is that a common approach you see in other areas?
I think so. I don't think that's a strange approach at all. I think more people should be doing it. I don't think it's as common as it could be, at least from the biological side. This might be different on the computational side.
And then Sebastian has a really interesting take when we start to talk about validation. I wanted to run that past you. If you encounter someone, maybe from your own field, someone comes up with a math model of tarantula behavior, how do you decide if that's a useful model or one that tells the truth in some way?
My hope would be that they had data with their model of real animals doing something so that they could validate how predictive it was of real behavior.
That makes sense. Yeah, that's kind of my instinct too. Sebastian has a slightly nuanced take on that I thought was really interesting and novel, so listeners should keep their ears perked for that. Recently, the world learned of the power of artificial intelligence, a technology cybersecurity leaders have been leveraging for years. Now, as AI expands and evolves, those same security leaders are left wondering where humans fit into the next generation of AI empowered security tools and solutions. Arctic Wolf, the industry leader in managing security operations, seeks to understand this question in the newly published report, The Human AI Partnership. Access the insights of over 800 cybersecurity decision makers in North America and the United Kingdom to better understand how organizations are weighing the benefits and risks of deploying AI tools. Uncover the biggest obstacles to turning AI and human engineers into a formidable team. Discover why the near-term benefits of large language models are being upended by a crucial flaw in the technology. And learn what the risks of AI tools mean for human practitioners moving forward. Get your copy of this report today at arcticwolf.com/dataskeptic. That's Arctic, ARCTIC, Wolf, WOLF.com/dataskeptic, all one word. arcticwolf.com/dataskeptic.
My name is Sebastian Moch. I'm an associate professor at ASU, working in the School of Mathematical and Statistical Science. So mostly I started to work on modeling complex systems. So usually it's called also like self-organized system. So the idea is to see if we can model, let's say, a particle system, like biological systems that's kind of like self-organized and create global pattern. So think about like a shoal of fish or a school of birds. So the goal is to try to understand how this emerged. So these global patterns emerge from normally simple interaction. How makes this kind of like whole, like bizarre, like crowd manage to nonetheless create some complex pattern?
I'm curious if we know much about where that pattern comes from. Like, did evolution give it to the birds, or do they have to teach it to each other?
Oh, that's a very, very hard question. Like, I'm only a mathematician, so
Sure.
that I cannot answer that. So here, what we try to do mathematically is to give different scenarios, so different possibilities. We're not necessarily going to answer like this is how they do it, or like how this nature select a certain behavior. So just the idea is to kind of give some key or like the complexity might be reduce some simple behavior. Whether or not like that's exactly how they do, that's more like for biologists to answer this question.
Sure. Well, you'd mentioned using things like particle systems. Does that mean you, in a flock of birds, you would model each individual bird?
That's the idea. So there's different approach when you do modeling. So ideally, that's what we want to do because we want to explain the global pattern. So you want to kind of like a physical system. You try to see that from local interaction, how this local interaction generates this global pattern. So ideally, yeah, we try to model things at a local scale. So how do, let's say, like two fish interact, and then you kind of scale that up to see how it's emerged. But that's not necessarily easy to do because I mean you need to track trajectories, and this is very hard. Especially, for instance, birds. It's even worse because it's in 3D. So how do you track that? I mean, there's many projects doing that. So sometimes you can go more like what we just described here. It's bottom up. So you try to go from particle to a large scale system, but sometimes you can even try to go directly like at the large scale system. So more like directly try to describe things like a fluid, for instance. So that's another approach. Ideally, yeah, I prefer personally go from particle to global scale, but it's not always possible.
So there's plenty of areas you might take influence from, like I think you mentioned fluid mechanics could be useful or something from it, perhaps. Is it along those lines, or do you have to invent new forms of equations?
I would say new form of equation nonetheless. The framework for my PhD, for instance, it was mostly based on so-called like kinetic theory. So if you maybe heard about that Boltzmann equation, so how
Mhm.
like collision between particles. So you can describe that relatively easily. So we can kind of mimic this idea, saying like two birds not necessarily going to collide, but they do some form of interaction that leads some form like change in the velocity. So you start with that, and then you can derive. So this framework here is really like kinetic theory to derive, let's say, fluid equation. So the equation are not the same, but I would say that the framework, the way we derive it, is kind of similar. So it's really based on this approach that has been done in fluid mechanics for quite some time.
Well, if you're going to model each individual bird in a flock, let's say, that bird has limits to its senses. Even though they have, much broader vision than we do, they can't necessarily see the entire flock all at once. There are local challenges to each individual bird. Is there a way that concept can become part of the model?
Yeah, that's the whole point. The whole point is to have particles that are not aware of the whole flock of birds. So they only interact locally, and nonetheless, with just local information, local interaction, you create some global pattern. And that's something that's not completely surprising. Like if you think about the fluid, for instance, like you can have like very complicated patterns, even though like a fluid, technically, it's just a bunch of particles interact with each other. So they don't see the whole fluid. So it's kind of like a similar patterns, a similar idea that with just local interaction, you can nonetheless create like global pattern.
Well, I will definitely refer listeners to look at the show notes for some of the equations. The equations don't necessarily work so well in audio format, but we can say some of the models are linear systems and they attempt to describe the behavior of the flock, or stop me if I've got that wrong.
Linear, which one not, I mean, usually linear is a little bit too simple. So when you say linear, typically that would be like you not necessarily interact with the others. So when you have linear interaction, like you can almost think about particular being independent. So usually it's more interesting mathematically when it's nonlinear. So there is some form of interactions. And that create like it's more complicated, but it's all more like complex at the end. So you have more like interesting patterns. So nonlinear, but otherwise it's perfect. Just nonlinear, and then we're good. Yeah.
Well, although that's a new side question, then typically when you go from linear to nonlinear, you lose all guarantees of convergence and quick approximation, things like that, because everything is differentiable anymore and all those sorts of challenges. Do you face a lot of computational challenges in the work?
Yeah. Convergence, that I'm not sure. So it's nonetheless, I mean, it's going to be well posed mathematically. I mean, not all of the equation, but most of the time. So what I just described here with particle system
Mhm.
takes the form of like a system of ordinary differential equation, and usually, unless you really want to make things horrible, it's well posed. Solution exists. Whether it to converge, more interesting question we have is what's happening when the number of particles goes to infinity. So it's a convergence, but not necessarily like in terms of time, but more like when we scale up. So you see, like you try to get to some, let's say, fluid equation. So the convergence here is not necessarily in time, but more like so kind of a two axis. Sorry, in radio it doesn't show up, but there's one is more like time, and the other one will be more like number of particles. So when number of particles goes to infinity, let's say, that's where you get your fluid dynamics. So this is where like we try to prove things, and this is very hard. So
Sure.
most of the time you can have formally like you derive, let's say, like some form. I don't know, for your listener are familiar, let's say some form of like I don't know, I would say like Euler equation or like Navier-Stokes-ish equation.
Uh huh.
Yeah, it's kind of thing. Yeah.
And is there any fit to the process, or is the model all you need?
That's a hard question. Ideally, what we start with, and you do some fitting to measure the individual behavior. So let's say like how fast do they travel, trying to see like how do they interact. So you need to have some experiment measurement. What's hard is afterwards is to see like, so you have your model, agent-based model, so particle interacting, you kind of derive mathematically your fluid equation, let's say. So take n very large. So you get the equation, you get some parameters that you can relate to the particle system. can you do prediction afterwards to see like this is really how like school of bird is behaving? That's really a hard question because basically we need n goes to infinity. So we will have to do like even experiment like in a setting where it's way larger scale, and that's really the I think the next challenge now.
Although there's something interesting about it that if you were to make a rendering of your flock behaving according to the model, I feel that if I saw a video of it, my eyes would either accept it or not accept it. It would say, this appears natural to me or it doesn't. So somehow I have a classifier in my mind of what's valid.
It's a very good point. And some actually, when we work with not necessarily biologists, that's really what they want when they do modeling school of birds. They don't necessarily want to see like how do they behave. Just want to look like birds, which is fine. But here that's part of the. I mean, to be honest, yeah, I would like to have my model like behaving like real birds. But the question might be a little bit different. So we don't necessarily want to reproduce what you see because, I mean, you already see that. So what do you need a model to reproduce what you see? It's more like to understand. So in the sense that can you understand what was the key mechanism responsible for this behavior? So sometimes actually it's good that we don't reproduce what's happening because you say like, oh, there's something missing, which is also informative. You don't necessarily want to reproduce because, yeah, if you just want to reproduce, just see what's happening. Like, you don't need a model for that. So really the idea of trying to understand what was a key element in your interaction that generate what you see at a global scale.
And would you describe your work as a form of swarm intelligence?
I don't like the word intelligence.
Yeah?
It's too broad. Yeah, it's too broad. Like same of artificial intelligence. Like nobody really know what does that mean. Intelligence. I like more the word emergent behavior. That's kind of like I think describe a little bit better in the sense that you really get to something you don't necessarily know firsthand. Let's get an example. For instance, you have meal formation in fish. So you all have seen that. So what does create this kind of meal formation? That's where really the challenge is. What kind of particular behavior will generate those patterns? Like, it's not like encoded in one fish. That's okay. Let's turn clockwise and do this kind of behavior.
Uh-huh.
So to see what kind of scenario, what kind of like mechanism lead to that, that's really what it's interesting. Yeah. Whether or not it's intelligence, I don't know, but it gives you some key to connect local and global behavior. That's about it.
So many swarm groups, one of the emergent behaviors that we'll see in them is that they'll all want to go in the same direction, let's say, and maybe even change direction. How does the group make that decision? How do they come to consensus?
You have to ask a biologist. I can tell you for my model we put that into account.
Yeah, according
But
to the model.
okay, the model. So the different approach. So maybe one of the most famous model is called like a Vic model. So the idea is pretty simple. You just take a local average. So you look at your neighbors, you make an average, where they're going, and just align with that. And so then you see like what happened at large scale, and it's not super surprising, but you have like kind of a phase transition if you put two elements. Let's say you have alignment, what I just described. You try to align with your group of neighbors, small groups, and then you also have some noise. And basically, there's a fight between these two elements. And let's say if alignment wins, you start to have like a global alignment. But then you can also like increase the noise, and then you kind of, alignment lose basically, and so it's more like swarming, let's say. So then you can have a balance. So that's for like something I work a lot on. So Vic model. You have a more like a simplified version, also like called the Kuckersmeyer model. It's kind of the same idea, but it's more a mathematician doing that. So what's nice is that it's simple model, but we can prove things. So mathematicians love the Kuckersmeyer model because we can prove like a theorem with a proof that they're going to align. So like you can prove things. Other type of model, more generally, more like let's say biologists, they like to call it like more like the three-zone model. So the idea is to have individual interacting in like three type of interaction. So if you're far away, you try to kind of attract, you try to get closer to your neighbors. If you're in a kind of intermediate distance, you just align. If you're too close, you go away. So that's why it's called like three-zone model. And from that, you can, with just this kind of three rules, you have like many patterns you can observe, flocking, for instance, but you can have meal formation, swarming. And so then the question is that which element, like which region you're going to create like a flock, in which region you're going to get a meal, etc. So there's like many studies along those lines. How you can predict, depending on the influence, the strength of those rules here, what pattern going to emerge.
Well, I know a couple of times you've been hesitant to let me say you're studying exact animal behavior. We're just talking about the model, and I get that. Is some of that just a desire to be scientifically appropriate, or are you disconnected from the animals? Or I guess another form of my question is, are there organisms in particular you're interested in?
Okay, so let me answer the first part.
Sure.
What I don't want to answer directly, because in biology, I mean, you have to be model specific. So I won't say like, okay, individual aligns this way or that way. It's really specific of which problem which system you study. For instance, ants, if you ants, fish, birds, they all behaving differently. So you don't want. It's not like a even for physical system, I guess it's a little bit similar. You don't want to have one fit for all model, saying that, oh, that the way things go, then I just tune my model depending on if it's an ant, if it's a bird, etc. You have to be more specific. I don't know if you want to say, for instance, for ants will react completely different than fish. So once you mentioned this study we did with Audrey Dussotour, I mean, they adapt way more like in traffic conditions. So if you have a heavy traffic, ants not really bother with that. I wouldn't say that's true for pedestrian, for instance. So it's really species dependent, I would say, the modeling.
Is there anything about ants in particular that make them a great subject to study?
Well, it's easier to do experiment with ants than, let's say, birds. Okay, so that's why also that's
Sure.
to start with. So you can do like many experiments, easy to record, to track the ant, etc. Easier to repeat experiments. Other groups find out is for traffic in ants is that I don't know if you know, like in traffic, usually there is a kind of a usual diagram. So you see the flow depending on the density. So usually when you increase the density, the flow increase, and then it start to goes down, and then it crash. You have a traffic jam. So usually like a bell curve, so like increase, and then boom, it crash because you have traffic jam. So what Audrey Dussotour find out is that this kind of curve is wrong for ants. Even if you increase like tenfold the density and somehow manage to maintain a flux that is not decreasing, let's say remain constant. So that's something like, okay, it's really experimental. No model will predict that. I mean, we afterwards try to do some modeling that explains this, but it's not the model that say like, oh yeah, look at what's happening in the model. No. It's really because of experiments, we start to go back and see like what's going on, like what is happening. And so that was something very specific with ants. Like, yeah, it seems like they'd be like, they're fine. Like you can put 10,000, I mean, not 10,000, but you can really overcrowded. So this experimental bridge overcrowded the bridge, and somehow they managed to, I don't know, maybe get on top of each other, whatever they do, but they managed nonetheless to pass. Something that we human cannot do.
Yeah, I wish our traffic flow departments could figure that one out. That'd be nice.
Sure.
And then what does data collection look like in working with ants?
Mostly videos. So you just basically you do the setup, and then you have like, for instance, for this particular experiment, I wish she would interview other researchers. She would explain better than me. But you play with a bridge. So the way you can get from very high density, you just reduce the size of the bridge. So the density, and immediately if you reduce the size of the bridge, the density increase, and that's how you can manage to have like very super like high density, even though the number of ants doesn't explode. So it remains the same number of the colony stays the same, but you just play with the size of the bridge, and so you can increase the density, and then you record. So you record them. What's very costly afterwards is that you need to track them. That's what you need, like a bunch of usually students. Okay, it's hard for them, so they need to track. And for instance, here they press every time they cross the bridge. You have somebody pressing +1, they go this way, -1 going that way, etc. You can do like more like software tracking, but when we start to have a very huge density, it's super hard because it go on top of each other. So if you try to track them, even though like I know machine learning is great and all that, it's still like maybe not completely like ready. I mean, I know like maybe you could ask Simon Garnier. So he's also a professor in New Jersey. So he's also doing like some form of tracking. So maybe he has a key to do that, but we were not to do that. So we had to manually like do the tracking for this particular experiment. For them, yeah, you can see that I don't have the name of the reference, but they can actually really like track automatically what's happening for inside the colony. So you have videos and tracking, so you can see all the trajectory. So that's super great, and it's very nice to have all this data that you can really do more than just like qualitative modeling and really quantitative analysis. Yeah.
And I wanted to get back to some of the dynamics and consensus stuff. Could you give us a definition of heterophilous and talk about its impact on consensus?
Okay, so that term, okay, as you can hear, I'm not English. I mean, I'm not native English speaker, so this is not from me. So this is my postdoc mentor, Ethan Talmor. We find out. So heterophilous, the way I describe it, is the fact that you are attracted more by some that have different opinions. So opinion dynamics, you just replace, let's say, velocity by opinion. Same idea. So you have your own opinion instead of velocity, and the idea is that if you have a consensus model, you look around, so who you're interacting with, and you kind of align with them. Whatever this opinion is, can be, let's say, a number, a vector, depending what you want to model. And so what we started to realize is that if you want to have like consensus, if you want to have like group of people like tend to get to the same opinion, it's better if you start to interact with people with have different opinions than you. So it's relatively easy to understand that if you only interact with people with the same opinion as you, you're gonna have like form some group of clusters. Some are very kind of almost identical opinion, but they stop interacting with those of different opinion. So the whole idea here in the way we model with Ethan Tadmore was to we do the same model, but somehow we put more weight when somebody has a different opinion than we do. So normally we try to align with people that are closer to you, and we just shift. We just only interact with the close, same. It's local interactions. We don't interact with people very far away, so still local interaction, but still we're more taking more into account those have a different opinion. By doing that here, you're more likely to get to a global consensus. So that's why we at Antam decide to use heterophilous dynamics. So we tend to be more influenced by those our different opinions than we are. And then we have more robust, more likely to get a consensus. So that's the idea behind heterophilous dynamics.
And then, so it's a interesting hypothesis in some sense that we would get a better group consensus. How does it pan out when you try it in simulation?
Yeah, so that's typically here that was really based on simulation. We can prove in certain cases, but this is very hard because well-posedness of models, that's not an issue. This is really that we just start to look at the other limits. So when time goes to infinity, can you show that it converges to a consensus? That's hard because it's all like local interaction. So initially, they don't all interacting. So if you at one point, even initially, let's say initially you have a group of people, some do not see each other, then it's very hard for them to reconnect at one point and form one consensus. So it's really depending also on the initial condition. But let's assume initially you have one way to connect with the other one, not if you don't talk directly to them, but through neighbors of neighbors of neighbors. So we say it's connected. So if you start with a connected initial condition, are you forming a consensus? Well, so here, this is where when we tune up this heterophilous dynamics, we start to put more weight with the neighbors that we are different from each other. If you look statistically, it's more likely that a consensus is going to occur. So we have numerical evidence for that. And in some situation, we can improve it, but we have to simplify the model even more.
So I'm a little confused by the need to take it to infinity. In animals, they can get to be pretty big, maybe tens of thousands of ants, but there's no infinity ants. And I feel like somewhere they would, turn into a black hole or something. Why do we need to go to infinity?
So here you're asking a mathematician. So I love n goes to infinity because it makes things simpler somehow. So we get what's called like PD. So we get a partial differential equation, and we can solve things or like analyze things I mean, we have a different way to analyze things. Maybe just to give you like a motivation.
Yeah.
A motivation, for instance, if you look at traffic. So I know cars are not going to infinity, but nonetheless, if you suppose like number of cars is very large, what you get usually it's a traffic model, and a traffic model what's very nice is that you can literally see traffic jam occurring. So you can even describe like how like you can have a shock or all this kind of thing. You need to describe that with a fluid model. So here's the traffic model, because you can analyze things, really analytically. We don't necessarily need to have simulation. You can literally look at the equation and say, okay, this is what's going to happen. So somehow here, it doesn't look like it, but when n goes to infinity, mathematically, it's somehow simpler. You can see things that you don't see when n is finite. Going back to your question, is this valid? So that is a little more up to debate, let's say. Mathematically, it's nice because we can analyze afterwards whether or not the limiting system, the PD, n goes to infinity, really still describing what's happening. That's I'm not so sure. So this is where the gap between experiment modeling is in math biology. It's quite challenging. It's not a physical system. I cannot say there's Newton equations, those valid equation. There's a kind of a faith when you do modeling. You suppose that this is what's going to happen. This is how they behave.
Well, when you look at how the local interactions will generate the global patterns, I get conceptually what that means, but I don't know intrinsically what a global pattern is.
So, for instance, you describe alignment. So, sometimes call it flocking, for instance. So that's, I would say, like a global behavior, or like meal formation. That would be another one, or I don't know, like traffic jam, shock. So this is more like from observing. So you have some typical observation that you see. Say, okay, this is what I want to get. It's kind of cheating, right? So the way usually you present things, we do like agent-based model, we derive some macroscopic model and say, oh wow, there is a pattern formation. It's kind of the other way around sometimes. You see a pattern and say, I want to get that. So what should be here is a local interaction that generates this pattern. It's not necessarily something like blindly say, we discover this is like a global pattern emerging. Well, we're kind of looking for that. So for going back to, let's say for swarming or flocking, so this typically you have try to describe in three simple pattern, like flocking, swarming, or like meaning. You can have others advertisement with some work I'm doing with Pedro Lowenstein. So with more we try to do streams. So instead of going all one direction, you can have going same direction but both way. So you have all the kind of pattern formation. That would be another one. But going back to your question, it's usually something you observe that you were to explain. It's not necessarily something we necessarily discover by solving the equation.
Could you share a few details about what's exciting and ongoing right now? Are there any open problems you're tackling or particular simulations you're working on?
So I think the next, would be very interesting to see next, that there is nonetheless a huge assumption. You haven't mentioned that yet. You were kind of intrigued by the n goes to infinity. The one that actually bothered me more than n going to infinity is the fact that we always assume that individuals are behaving the same. So we always assume, most of those models, that's okay. We have agents, whatever we call them, and they're behaving the same. Well, that's a huge assumption. There's a lot of variety among individual. Can we use that also? I don't know how we deal with this kind of variability among individual. And this is where it starts to be challenging even from a modeling perspective, because I can always make model more complicated. So I have more degree of freedom, etc. So the issue then is that, okay, but then it becomes too complex. If you have for each individual, you have tens of, parameter for each individual, what are you predicting at one point? You just you have too many degree of freedom. So you don't really explain things. You just start to just reproduce.
Overfit.
Yeah, so you have overfitting. And I think so now what we kind of have a competition with, modeling. I don't know if I can call modeling, but going more for machine learning, purely data-driven approach. We say hey, let's forget about model. Who needs model? We have the data now. We have those neural networks. Let's just apply that to do prediction. And I think we start to have, I still internally, I start to have competition between going more mathematical approach, like PD, all the stuff I like, and now saying okay, who cares? They give me the data, give me some stuff you want to see, and I have a kind of a competition between the two approach. Purely data-driven and more I would say traditional, going back to modeling. So it's more physics inspired, let's say, approach compared to purely data-driven approach. I think that's where there's a start of a fight between the two approaches.
Is it possible to meet in the middle?
Well, that's what I'm trying to do. But it's funny that actually when I talk with biologists, Biology seems to be more, they really like modeling approach, not necessarily a data-driven approach. Somehow here, when they try to understand things, they know that the model doesn't reflect really what's happening. And that's not necessarily the goal to reproduce, because again, I mean, if you just want to reproduce, what can be better than experiments? That's the best. So the ideas have to do like modeling because they give an idea about what possible scenario, how a thing could work. When you do purely data-driven approach, so I don't know, you just like record all the trajectory and you don't even try to put a model, just say, okay, let's try to see if that generates this pattern, etc. It's really just to have a black box. So you don't necessarily like understand what's going on. That being said, I like the data-driven approach nonetheless because I feel sometimes it's fair. Like you don't try to necessarily like have a pretty model. Don't care about this. You just okay, that's fine. I want to see this pattern forming here. Give me the data, and I'll try to do that. Do I need a model? That's my internal fight that I have right now.
Do you think, in particular, anything from the recent advancements in AI could bring innovation to your style of modeling?
First thing, for sure, not necessarily modeling, but for instance, to collecting data, it's a huge plus. For instance, what we're doing right now with Audrey Dussoto, we shift from ants to slime mold, so very different things. But here we're using AI or machine learning a lot because to track, to do all this kind of segmentation, etc. I mean, it's superb now. You can collect data much better way. Now, in terms of modeling, that's what's a little bit difficult when you do modeling animal behavior. It's what do you try to explain? So, what do you try to achieve with a model? If you just try to reproduce, and yeah, I mean, you have data, who cares? What would be nice is really to identify. What I really like to have is to have more like Kaggle competition, for instance, for modeling animal behavior. That would be great. I would like to have like a fair fight. Right now, I feel like it's whoever presenting the better could kind of like famous, let's say, modeling, famous approach, saying like, okay, look, like it's very elegant, or like I don't know, like I don't know what would be actually a good criteria for if you do pure data-driven approach. But it would be nice to have like a fair competition. Say like, okay, fine, okay, those are the trajectories. This is what I would try to explain mid formation. It would be nice to have such things. I don't know, like right now, like if I don't have any competition like around this line.
I've never seen that, but yeah, that would be really cool.
Yeah.
Well, you mentioned also working with slime molds. I think of them as one of the least complex organisms. Maybe that's my bias. What are the emergent behaviors that drew your attention to slime molds?
So again, I'm going to refer to Audrey Dussoto because I'm not an expert at all in slime mold. But the idea here is to understand the so-called, like, I don't know how to translate it actually in English. In French, is prise de décision. So when you take a decision. So at one point, when you see slime mold growing, sometimes you see that there is the growing can maybe just like I don't know, like think about a balloon expanding. I mean, it's 2D, right? But you think about a disc extending, and suddenly, like boom, something like pop up and decide there's a branch that start to grow in one particular direction. What happened? What at one point, like you have decision making, saying like, oh, let's go this way. How do you explain this behavior? As you said, like you said, it's super simple. Like there's no like complicated I don't know, like neurons, whatever. It's just one cell, actually, this whole slime mold. So, nonetheless, if you think about like modeling, it's a mystery. Like I don't know, like how you can have suddenly like this kind of pattern, like you have a break of symmetry if you want. It was kind of circular, and suddenly like boom, there is something like expanding in one direction. How do you explain such things? Again, so what do you do? Like, do you do like purely data-driven approach? So you look at all those video experiment and try to see like can you predict just based on those video like what's going to happen next, or can you do some more like modeling? But here I don't even know how to start because there's no particles here. So maybe the mixture between like a fluid or like something in between. So yeah. How do you explain this break of symmetry? That's the next challenge.
Do you have advice for aspiring young students looking to get into similar areas?
Learn Python. Okay, so that would be my first advice. So, especially in math, because I know in math we mostly like by I don't know. There's some form of inertia. We usually go like MATLAB and stuff like that. I usually do Python because right now I think like we have like data-driven approach, machine learning, etc. So you need to know Python somewhere or another. So that's for more like mathematicians. The other advice, I think, like, yeah, anything stochastic related start to get more and more important here. Not that I don't like PD, fluid mechanics, but I feel like right now more and more we need people knowing a lot of statistics, so stochastic differential equations, this kind of stuff. I think that, yeah, that's. I wish I would have taken more class, let's say, in probability and statistics.
Well, Sebastian, thank you so much for taking the time to come on and share your work.
Well, thank you, Kyle.